Good morning, dear students, and welcome to Vista's Learning and online educational platform. My name is Denzil, your physics tutor for class 11. So let's begin with our topic for today. Our discussion for today will be based on a concept called relative velocity. This is a session 6 of the chapter Motion in a Straight Line. In the previous chapter, we discussed a couple of physical quantities such as distance, displacement, speed, velocity, and also acceleration. We categorize these physical quantity under two such which are called as a scalar and a vector quantity. And the reason why we do that is because certain physical quantities have magnitude but no direction. And those quantities are called scalars. Quantities which have both magnitude and direction are called vector quantities. And then in the last session, session number 5, we derived three equations of motion. We saw the relation between position and time, velocity and time, and also velocity and acceleration. So these were the things that we discussed in the previous session, but in this session I have the same derivation but except in a different format. So let's get started with this question where I left off. So here we have to obtain the equation of motion using the method of calculus. Again, I hope you've gone through the revision of a calculus where I've conducted a bridge course. So let's get started in deriving those three equations of motion using calculus. You ready? Let's get started. So first we begin with a definition for acceleration. Acceleration is defined, pick a color. Acceleration is defined as the rate of change in velocity. This rate of change in velocity can be written as dv by dt as a differential equation. Now what we do is these two dv and dt, the variables, dt I transpose it to the left hand side, dv I keep it as it is on the right hand side. So I get a times dt, which is equals to dv. Now don't commit this mistake where you try to cancel d and just write v by t. Now why can't you cancel the letter d and d? That's because in a differential equation, these have a meaning to show it is the derivative. A difference in the velocity and the difference in time where you add a certain limit to that denominator. Where the denominator limit is where delta t is tending to 0. Now try not to cancel because it's a big blunder to do that. To put it in a simpler format, think of it as a tool. Okay, this is a tool in mathematics, you just cannot cancel it. So now I've sent the dt transpose it to the right hand side, to the left hand side, or my right hand side rather. Next, I will use another tool in mathematics which you will be soon learning called integral calculus. I have given an introduction to differential calculus as a bridge course. Integral calculus will conduct it later, but bear with me, have a look at how integration works. So for a given integral calculus, you represent it by that symbol. Okay? You integrate on both the sides. So let's mention that integrating on both sides. BS is not what you think it is. It means both sides in mathematics. So now that we have integral, we are integrating it with respect to dt. Similarly here, we are integrating with respect to dv. Therefore, it has a certain limit that you can assign. The limit for time, let's say it begins from a 0 to a particular time t. On the other hand, dv, let's say, which is the velocity, initial velocity be represented by vi, final velocity be represented by vf. Now that you have to integrate, you have to only integrate it with respect to time. So you do not consider a, this acceleration becomes a constant, so you can take that a outside, and you're integrating that left hand side with respect to dt, and on the right hand side you're integrating it with respect to dv. And by integration, what you obtain is a times t under the limit 0 to t, which is equals to, oh, I didn't write dv here, dv. Integration of a dv is just v under the limit vi to vf. So now that we have integrated and obtained the solution, we have to apply the limits. So to apply the limits, always remember it is the upper limit minus the lower limit. Upper limit minus the lower limit. So you get a t minus 0 is equals to vf minus vi. Alright, and finally t minus 0, any number subtracted to 0 will be the number itself. So 1 minus 0 is 1, 2 minus 0 is 2, 3 minus 0 is 3, t minus 0 is t. So at, which is equals to vf minus vi, transpose the vi to the left hand side and you get at plus vi equals to vf. Ta-da! This is your first equation of motion by using calculus. Now how many more? 2 more. So bear with me, we've got 2 more, but I'll simplify it as much as I can. All you have to do is write them in your notebook and practice it for later. Okay? So moving on to the next one. For the next equation of motion, we consider the definition of velocity, where velocity of a given object is the rate in change in position of an object, a rate at which the object's position changes. So dx by dt. Just like how we notice for an acceleration, we transpose that dt to the other side, so you get v dt equals to dx. Do you recollect the first equation of motion where we mentioned vf equals to vi plus at, correct? Now this vf is nothing but v. So in place of this v, I will substitute vi plus at. So vi plus at. Oops. A-L-L. At into dt is equals to dx. So I put this in a bracket because it's one common expression, vi plus at. Now we integrate on both the sides, just like the tool that we used in previous case, the similar tool we use here. dt, you integrate it with respect to t, integrate it with respect to dx. First, integrating with respect to t under the limit 0 to t. So it starts from 0 and as time progresses, finally it ends at time t. Similarly, you have dx, let's say initial displacement, initial position, we'll write it as xi. Final position is xf. All right. Now the fun part here is, since this expression is within a bracket and dt is outside, we have to multiply dt within the bracket, meaning you will be applying this integral tool to each and every single expression within. So multiplying it, you get 0 to t vi dt plus 0 to t at dt, which is equals to, see, you applied the tool for all the individual variables that are within the brackets. Now on the right hand side you have xi xf dx. Now you need to integrate. So I will do that for you. I will integrate for now, but later stages you will learn them in mathematics. What are the rules of integration? I will, however, conduct a bridge course to teach you how to integrate and what truly integration is all about. So under the limit 0 to t, and then at, the integration of at in this case, so just like the previous, a is a constant, so we take it outside because you have to integrate only with respect to t. So what you end with is a t square by 2, again under the limit 0 to t, and this is just dx. So x under the limit xi to xf. All right. Now we apply the limits. Upper limit minus the lower limit only to t. You apply to t. All right. So t minus 0 plus a t square minus 0 square. Why is it t square? It's because the expression itself is t square, and when you apply the limit you need to square that limit, the upper limit and the lower limit, and then the common term, which is 2, and that, which is equals to xf minus xi. T minus 0 is t, so vi times t plus 1 by 2 a t square is equals to xf minus xi. Is it looking familiar? This is almost similar to what we had derived in the last session, the equation of motion, the second equation of motion, position and time relation, right? So now you can transpose that xi to this side, and you get the final position of an object. This is how you derive the second equation of motion using calculus. All right. And now finally we come to the third equation of motion. So let's deal with the third equation of motion. Third equation of motion, we consider the definition of acceleration as the rate of change in velocity of an object. Now here, have a look at this, pay attention. Now dv by dt can be written as dv by dx and dx by dt. You see that what I've done is multiplied and divided dx, and I've written as dv by dx and dx by dt. Why? Is because we know what is dx by dt. What is dx by dt? The rate at which an object's position changes is called velocity. So A, which is equals to V dV by dx. dV and V. So you have V, the variable V which are located here. So I let the variable V remain on the right hand side, but this dx transpose it to the left hand side. So you get A dx equals to V dV. Integrate them. You're integrating it with respect to x. Therefore, xi, xf be its initial position and the final position. Vi, vf be the initial velocity and the final velocity. By integrating, you get ax under the limit xi to xf, which is equals to v dv, and upon integrating you get v square by 2 under the limit vi vf. Okay, now you apply the limits again. Upper limit minus the lower limit is how you apply. So a x f minus xi is equals to 1 by 2 times Vf square minus Vi square. You can transpose the 2 to the other side. 2axf minus xi, which is equals to Vf square minus Vi square. Transpose the Vi square to the left hand side and you get 2axf minus xi plus Vi square equals to Vf square. This is your third equation of motion that tells you the relation between a position and a velocity. Okay, now we have successfully derived the three equation of motion, where you have V equals to U plus AT, but in this case I've written as VF equals to VI plus AT. And then the second equation of motion, XF equals to VIT plus half AT square plus XI, or simply you would have learned it in your 9th standard as S equals to UT plus half AT square, right? So it's a similar expression. And then you have the final expression, which is 2a xf minus xi plus vi square equals to vf square. So this is similar to what you had learned as v square equals to u square plus 2as. So, but the derivation was by a method that is called calculus. So now we move on to the following topic, which is a free fall. Free fall, an object that is falling by itself under influence of, let's say, an object which is like a ball. Now, holding this ball on my hand, you see it is stationary. But once I let go of the ball, it falls to the ground. Now you tell me, under what influence does the ball fall? Now certainly, I did not push the ball down. I did not see the angels pushing the ball down. So what could be the reason why the ball falls to the ground? And if your guess is gravity, that is very good. Yes, due to the gravitational force of attraction, that is because of the mass of Earth. So gravitational force of the Earth, it exerts a certain force where it attracts every single object towards the center of the Earth. So we can mention this is under the influence of gravity. Objects fall to the ground under the influence of gravity. Now, while they fall to the ground, an object which is initially dropped, its velocity is 0. So we can confidently say that the initial velocity of the ball is 0. So initial velocity of the ball is 0. What about its final velocity? As this ball was dropped, what about its final velocity? Was it 0? Certainly not, isn't it? As the ball falls to the ground, it increases its velocity, changes its velocity. So, final velocity is not equals to 0 for those objects which are said to be falling under the influence of gravity. These objects which fall under the influence of gravity are what are called as free fall. Okay? So now that we have seen the initial velocity of the ball is 0, but the final velocity of the ball is not equals to 0. So there's a change in velocity. And whenever there's a change in velocity, the rate at which the velocity changes is what is called as an acceleration. In fact, this acceleration as the ball is dropped is a constant. And this constant acceleration is called gravitational acceleration due to gravity or gravitational acceleration. So we say acceleration due to gravity. It is given by the small letter g, whose unit is meter per second square, just as acceleration. We denote it by g to show that it is the acceleration due to gravity. Any object that falls under the influence of gravity, its velocity changes, and the rate at which the velocity changes is a constant. Therefore, this constant is given by g. Now, what about its value? Can we identify its value? Certainly, yes. Its value can be identified. Now, there are different methods as to how you can identify this constant value g. And one of the methods that you'll soon be learning is by using a simple pendulum. By using a simple pendulum to determine the acceleration due to gravity. Now, why did I bring this up is because remember the three equations of motion? In those equations of motion, we have acceleration as a term that is put in the given equation. Now that acceleration has to be substituted for acceleration due to gravity. So let's have a look at it. Now for objects that are falling down, okay, objects which are falling down, the equation of motion can be modified. First, let me write the original equation of motion. What is the original equation of motions? Equations of motion. 1. What is this? V equals to, let me write it in a simplified manner how you have learned it in your 9th standard, so that even by substituting you're still able to recognize. But if you want me to write by Vf and Vi, I'm much more comfortable doing. So let me write it by Vf by Vi since we have moved it to our next higher classes. So Vf equals to Vi plus At. Second equation of motion is S equals to S equals to Vi T plus half At square, and the third equation of motion is Vf square equals to Vi square plus 2As. Now in place of A, as you notice, what will I substitute it with? Acceleration due to gravity g. For objects that are falling down, the acceleration due to gravity g has to be substituted. So let's substitute and we get gd. See, a simple. Very simple. All you have to do is substitute in place of a, g. So then the second equation of motion is S is equals to VIT plus half GT square. Now, one more interesting fact is, for a free fall, initial velocity is zero, meaning Vi usually are zero. So if this is zero, what you're left out with is half GT square. Okay, and then a third equation of motion, which is Vf square equals to Vi square plus 2 Gs. Okay, now this is particularly for objects that are falling down. Now we'll look at objects that are moving up. How do I have to substitute my acceleration due to gravity? For that, we have to analyze this diagram, this animation once again. Initial velocity is zero, and as the object falls to the ground, I've stopped at a certain interval, but in that certain interval, the final velocity is not equals to zero. So as the object is falling down, its velocity is increasing. Due to its increasing velocity, we can confidently say that acceleration, so there is an acceleration, so it is speeding up. But what happens if I throw the object upward? Yes, when I throw the object upward, the velocity of that object will slow down. It decreases as it moves upward, and it reaches a final point where its final velocity would be just zero. So you can try this, where you try to throw an object upward. You will notice its velocity will reduce, and at a certain height the velocity would be zero. Here we notice the case where a deceleration or a retardation occurs. In simple words, let's say negative acceleration. So you have a positive acceleration downwards and negative acceleration upwards. Therefore, for objects that are moving up, for objects that are moving up, how do I modify the equation of motion? The first equation of motion would be Vf equals to Vi minus Gt. Notice the sign has turned into minus. In the previous case, plus, and now it is minus because the object is moving up. Now, the next one is S equals to Vit minus half Gt square. But this is not for an object under free fall. Okay, let's remove that. This is not for an object under free fall. So, will Vi be zero in this case as you throw object upward? No. Vi cannot be zero. There is a certain initial velocity, but the final velocity as it reaches up is zero. Next, the third equation of motion final is Vf square equals to Vi square minus 2 Gs. So make note of these three equations of motion for objects that are traveling up, and also three equations of motion for objects that are traveling down, and this particular is for objects that are under free fall. All right. Okay. So here's a quick question. So I'll erase this part. So for objects that are usually under free fall, when it is released from rest at y equals to 0. Therefore, v naught is 0. V naught here is the initial velocity. And the equation of motion become, so again, object is released from rest at y equals to 0. How is that you release an object when you have a zeroth position? Think of it as a graph sheet, and within a graph sheet you have this two mutually perpendicular axes that is drawn. At zeroth position you have a box that is located, but as you travel upward you have all set of positive integers such as 1, 2, 3, 4 and so on and so forth. As you travel downwards from 0, you get set of all negative integers. -1, -2, -3, -4 and so on and so forth. So now this object is released at a position y equals to 0. At this point, initial velocity is 0. So what happens to the equation of motion? Let's take a look at it. In the first equation of motion, when v naught, the initial velocity, is 0, now you get 0 minus gt, where you get g value. Oh, I have not mentioned the g value. So even in the previous case, the g value, acceleration due to gravity, its value is, g value is 9.8 meter per second square. How will you identify this? You will soon be conducting an experiment called simple pendulum. There you determine the acceleration due to gravity, g value, which is roughly about 9.8 meter per second square. All right, so same thing that's mentioned here. So for this, we will plot a graph. We will plot a graph. So here's the graph that's been plotted, where you have acceleration time that is mentioned. Notice the acceleration is roughly about minus 9.8 meter per second square. Now why is that g value, why is that the g value is taken negative 9.8 meter per second square? This is for convenience sake, because on a number line, we know if a number line which is in a vertical position, we know objects that move upward are usually positive. Objects that move downward are usually negative. So here for an object which is under free fall, we can consider that g value should also be negative because it is going through a negative displacement. And that is why, for convenience, we take g value minus 9.8 meter per second square. Similarly, using the same set of information for the second equation of motion. But here you have y being the displacement, there we have written s. No problem. 0 minus initial velocity 0 minus half gt square. You get minus 4.9 t square. And then we try to plot a graph that is velocity versus time. And when you plot a graph velocity versus time, you get a linear curve. A linear curve, but here you see that you have a horizontal line which is parallel to the time axis. A constant value. Changing curve. Now let's do the same thing for the third equation of motion. And this is for third equation of motion. Final velocity, initial velocity is still 0, 2gy. G value is 9.8. And then by substituting, you get minus 19.6 y meter square per second square. So after obtaining this, we plot them in a graph of distance and time. And when you plot for that acceleration, you get this beautiful curve, which is a parabolic path. All right. So this is how you can identify the acceleration due to gravity A or G by the following method: substituting and finding them in an equation form and also in a graphical format. Now coming to our main important topic, which is relative velocity. Have you ever had that experience where you're sitting near the window seat of a train and you watch another train that is passing by? And by the way, you and the neighboring train, your train and the neighboring train, let's say, are moving along the same direction, same velocity. And when that happens, when you look at the neighboring train, you feel both the trains are stationary. Have you ever had that experience? It's more like this cat. Assuming that both trains are moving, but when this cat looks into the neighboring train, it seems as though both the trains are at rest. But for a person who is outside, the observer who is outside will see the difference that these two trains are actually in motion. Let's take a look at it from an outside perspective. So you be the observer. Now you watch. Okay, we start this train. So you watch this train both move together. All right. So I'll step out of the frame, have a look at it one more time. So you notice these two trains move together. But for perspective, which is outside, both are moving. But for the cat who was sitting inside, both the trains were at rest. So to identify this feature as to velocity of one object with respect to the other object, how can we identify a velocity of one object with respect to other object? Let's take the case of a train. Let's say you have train A and train B. Initially at rest at time t equals to 0. To note down their position at any given instant of time, I'll step there. At any given instant of time, let's say for a train B, at any given instant, to make a note of its position, then you try to identify the position of train B at time t equals to 0 plus velocity of train B times the time. For those of you who are finding it difficult, it's very simple idea as VB equals to XBT minus X B naught divided by T. Change in position divided by time. And by equating it, you can write it in that manner. Okay, for those of you who are finding it difficult to understand this, it's just the definition of a velocity of train B, change in the position in train B, final position minus the initial position divided by time t. You may ask the question, then why is it written as xb of t? That's because here we're showing that this position is a function of time. Okay. Similarly, we deal with A. So I'll erase this part now. Position of A at any given instant of time. Stop train, don't move. Position of A at any given instant of time, which is equals to position of A at time t equals to 0 plus VA of t. To identify what? The position of one train, let's say B, with respect to A. Meaning, let the observer, which is the cat, be sitting in train A and he makes note of the position of that train B. how much of a distance has it covered. So that would be xb minus xa. Do you know the value for xb or the equation? Yes, you know this is what xb relation, this is what xb stands for, and this is what xa stands for. So you substitute plus vbt, vb. Now when I'm writing b, it is suffix b, all right, to show you the velocity of a train, b. T minus, here comes the fun part. When you write this, make sure you write it within a bracket because you have to conduct a sign multiplication. All right. All right. So, all right, choo-choo train, you can move to the other side. So you can wave goodbye to those choo-choo trains. Now we substitute xa of 0 plus va of t. Now you do the sign multiplication. Bring all the xb and xa of 0 on one side. xb minus xb naught minus xa naught plus vb minus va of time t. That is after the sign multiplication. I've taken the common terms. So this is how you identify the position of one object with respect to the other observer A. So we can say that VBA, velocity of BA, which is equals to velocity of B minus the velocity of A. So we can also look at this by a graphical representation. Okay, let's have a look at this by a graphical representation. Okay, I might have to erase. So you have time that is represented on one axis, x, distance on the other axis, the y-axis. So since they have the same velocity, the inclination for A and B both will be the same. So this is to show you that A and B have the same velocity. Though the positions may be different, but they have the same velocity. Therefore, when this cat looks into the other way, looks at the neighboring train, it appears as though the train is stationary because the two velocities cancel each other, as a relation that we had mentioned, that VBA, which is equals to VB minus VA. Since both the velocities are equal, what happens is that you get 0. Because VB equals to VA. Now, let's take a look at another scenario, but in this case, the train appears to be moving for the cat. It is not too fast. The train that the cat is actually traveling is also moving, but the neighboring train is also moving, but not very fast. It may be moving a little slow. So what is happening here? Now for a perspective that is outside perspective for you, you may take a look at the train, these two trains called train A and train B. When they both leave the station, they are not necessarily traveling at the same speed. One's velocity might be greater than the other. So have a look at that and you notice B's velocity is greater than A. So I'll step out of the frame one more time. And therefore, for the cat, it appears that the train is actually moving slowly. Even though for you, the train was very fast compared to the other, but for the cat, it only appears to be a small movement. So how do we interpret this using a graph? So using a graph, you will notice that for train A and train B, the same type of graph where you have x represented on one axis, time on the other axis, they both intersect at a single, meaning they both meet at a single point. Train A, train B will both meet at a single point, which is at time 3 seconds. Now there's also another final type of a type where we can represent this relative velocity. Now the motion of a train is in the opposite direction. You witness this motion of a train is in the opposite direction. Now for the outside perspective, this train, I'll step out of the frame, have a look at this now. So these two trains are passing each other. So meaning they meet at a given point. Can this be represented by a graph? Certainly. So you have a graph again x and t. So the direction of one train is in a positive direction, the direction of the other train is in the negative direction. But recollect in the previous, when two trains were moving along the same direction, there both of them they increase along the same direction, which is of the positive. Now since they're passing in an opposite direction, therefore they meet at a single point, okay, at a given time, in this case 1 second. So yes, this is pretty much about relative velocity of an object. We shall discuss a little more detail about relative velocity and problems that are related to relative velocity. I hope you've enjoyed the video. Make sure you visit us at www.we-learning.in to get more details about the classes. I will see you all in the next session. In the next session, we deal with question and answers. So bye everyone, take care and have a nice day.